Have I not been streaming this whole time? All right, hold up, everybody. I need to check this out. I wonder if I just had stopped it. Oh no, I did talk about it. Okay. This is gonna be weird. I'm gonna have to look at where I finished on this. Did I get through all that fun stuff? Oh, I didn't. Okay, my bad. I'll fix this. I think when I was trying to share that screen, I accidentally clicked stop streaming. So, whoops. And now look, now the tablet's gone away. Okay, so let's go back to that Wikipedia page so we can see that. All right, we're gonna go here. I'm not gonna click stop streaming. So these are some numbers for us to look at. The numbers are not terribly important. We can kind of make that approximation, but we're going to see that the numbers are not really that important. We're looking at trends here. So what I want us to look at is, let's look at period 2. Let's look at lithium versus beryllium. We expect, because lithium has 1 valence electron, beryllium has 2, that it's going to increase, right, from left to right. And indeed, as we increase from left to right across the periodic table, our effective nuclear charge increases. So as we go left to right, we increase. All right? That's important. And I want us to also see what happens as we go down the periodic table. So hydrogen is standardized at 1. Then we can go ahead and look at lithium, 1.2, sodium, 2.5, potassium, 3.5, rubidium, about 5. Notice, by the way, we're always looking at the outermost electrons, so that's why I'm going with the last ones here. So that's what we're looking at here. And so with this, we are understanding that we have 2 trends that we see here. We have, as we go left to right, things increase. Again, we can take a look here. We can see this increase as we go left to right. Oh, that's the d electrons. We don't care about them. As we go left to right, things increase. All right, and as we go down, things increase. All right, let's switch back to the tablet. All right, and of course the tablet is not projecting. Hold up. It's going to be that kind of day, isn't it? Okay, so where were we? So here's our trend. So we see that effective nuclear charge increases as we go to the right, and it increases down. So periodic table, we're going to have a lot of these drawn this week. We're going to see that Z effective increases as we go left to right, and it also will increase as we go down. So we're expecting oganesson here to probably have the greatest effective nuclear charge. Oganesson is the bottom right corner. So it increases as we go left to right, and increases as we go down. The reasons for that, of course, we simply have more protons in our nucleus with the same shells, so things get pulled closer. Things are felt more because we have more protons as we increase left to right. And let's write these down. It increases to the right because we simply have more protons. So more protons in your nucleus means bigger charge, right? And we see that as we go down, we also are increasing protons. So we still have that, but we also need to consider that the farther out we go, which is kind of just like outer and outer shells, as the shells get bigger and bigger, the electrons are more dispersed. And so that means there's less repulsion happening. If you want to consider, we can switch, cool, Bohr model. Let's say I've got 5 electrons here versus 5 electrons there. Obviously, the ones on the left are going to have more repulsion, right? So the ones on the right, because they're farther out, there's more space for them. And so as a result, there's less repulsion. So that also increases your effective nuclear charge because you have less competition for it, essentially. So the nucleus can send out its happy positive rays and all the electrons can be happy. So we see typically that that this is just kind of a pretty straight increase as we increase our atomic number. So more protons, and then the bigger our atoms get. I guess that's a hint. But you can see the more shells you have, the bigger things are going to be. So we have 2 reasons there that the effective nuclear charge increases. All right, how's that? Any questions on that part of this? Do we even have streamers or people watching today? That's the real question. Because I know you're all probably still watching the last videos. Indeed we do not. How very sad. Oh well. Okay. Cool. Well, then that means I could just keep on going. So, that's effective nuclear charge. So increases to the right and increases down. All right, so next we're going to look at atomic size. And this can be described as the radius, the volume, anything you want to talk about related to size of atoms. We're looking at the radius, the volume, whatever, surface area. I mean, that's a little weirder, but that's what we're looking at here. And so we're going to see that the first consideration we're going to look at is the number of shells. As n increases, size increases. And hopefully that makes sense. Here's our Bohr model. Here's a hydrogen, here's a lithium. Hopefully we can see the lithium is bigger. We have more shells. Pretty standard, right? Remember that, this would be the 2s shell on lithium. It's also got the 1s inside it, right? The 2s is farther out from the nucleus, it's higher energy. And so, as a result, because it's farther out, that's going to make our atomic size bigger. So, I swear there's like a truck idling right outside my window. I hope that's not making too much noise. So, this trend is pretty obvious. So, we're going to see, look, here's the sodium. As we go down a periodic table, ET periodic table. I'll use that a lot, I think, today. As we go down the periodic table, our size increases. And that should be hopefully pretty self-explanatory. The more shells you have, the bigger your atom is going to be. pretty standard. But what's going to happen as we go left to right or right to left? That might not be so obvious to us. What about as we go left? How does that change? Well, this deals with effective nuclear charge, which increases to the right. Well, I should say left to right, shouldn't I? So we are at least consistent. As we go to the right on the periodic table, we want to remember that effective nuclear charge increases. And we're going to see yeah, I can do it for these two. Here's our hydrogen, here's our helium. This electron feels about +1 in terms of charge. And in fact, it's not about, it's defined for us. Helium we saw was about like 1.6, but we'll say it feels about +2, these electrons. And so, this means that there's more attraction, which means that it's more likely to be close to the nucleus. And as a result, the shell gets pulled into the nucleus, towards the nucleus. All that means smaller atom. And indeed, we are going to see that helium is the smallest of all of our atoms. So it has the fewest number of shells, and it has the highest effective nuclear charge within its own number of shells. So as a result, we can kind of condense the shell towards nucleus. All right, and so we're going to see that the atomic size decreases from left to right, and the atomic size increases as we go down. That means so size is going to increase to the left and increase down. Which means that francium here is our largest element. And helium here is the smallest. And I have numbers for us here as well. Atomic radius. Oh, I have to choose which type. Yeah. These are covalent radii. I don't want those. Calculated atomic radii. That's what I want. All right, so here we go. Switching back to the screen. Let's hope I don't stop the stream again. Aha! So we're looking at atomic radii. These are in picometers. We see that the trend is as we go down in a group, wow, I can't highlight everything. Okay, but as we go down, 243, 265, 298, as we go down, we are increasing our size. And as we go from right to left, I suppose, we are decreasing. Or, no, right to left, we are increasing. So 38, 42, 48, 56, 67, 87, 112, 167. We see indeed helium is our smallest over here at 31 picometers. And while we don't really have a number for francium, it would theoretically be the largest. But since we don't have francium, cesium will be our largest. So I guess they have not bothered. I guess maybe those weren't discovered by then. So we see here the trend. Biggest one is going to be bottom left. Smallest one is top right. And so everything follows the same trend here. So again, these trends are very handy and they're very reliable. Just looking at this, I don't even see a single exception as we go from right to left and down. So cool stuff. Yes? So those are atomic radii for us. So with those, let's talk about ionic radius now. So these are just atoms. These are atomic radius. Let's switch back to the thing. Okay, cool. So these were atomic size, regular atoms. But let's see what happens when we make ions out of things. So this was for atoms, which of course were neutral. But what about ions? What happens to an atom when it gains or loses an electron? What's going to happen to it? So when an atom loses an electron, aka sodium losing its electron, it gets much smaller. Because we're going from what is this, neon 3s1 to neon. Right? That's effectively what's happening, right? In terms of this kind of reaction, this losing of the electron will turn us from neon 3s1 to neon, electron configuration-wise. But sodium has 11 protons, whereas neon has only 10. And if they have the same electron configuration, we're going to see that more protons means we're going to have a greater effective nuclear charge, right? And so as a result, even though they're both the same electron configuration now, the sodium ones are going to be pulled in a lot closer than the neons will be. And so the electrons are pulled in even more than neons would be, because it's got more protons. And so we've lost a shell, which is awesome. So we've shed our shell there. We've lost it, and so now we're going to be much, much smaller. And in just a sec, we'll look at some numbers, just so we can have some values to put with these. But that's what we're looking at here. So when we've lost our protons, lost our electrons, and so because we have more protons now than the corresponding noble gas, Remember that the elements will kind of always tend towards noble gas configurations. That's what happens. We end up getting smaller. Then, of course, we have the opposite. Inversely, when atoms gain electrons, they get bigger. So, as chlorine becomes chloride, as it gains an electron there, as chlorine gains an electron, we're going from, what are we, 3s2, 3p5, sounds about right, to now being, what's the next one, argon. All right, and so they both have argon's electron configuration, but Cl has 17 protons. Argon has 18 protons. So chlorine is still going to be bigger than argon, because you have fewer protons and the same number of electrons. So all those electrons are going to repel each other more, because we're cramming in extra electrons and we don't have enough protons to attract them in. And so as a result, we end up getting an increase in the size of our element. And so let's go ahead and take a look at some numbers. Let's ionic radius. See some numbers here. Okay, well, it's this will work. Wikipedia thankfully has all the numbers we could ever need. So the ionic radius for some of these elements, as we look at them, let's take a look at sodium. Sodium's ionic radius is 116. What I should have, I don't have the, I do, okay. Oops. Notice that sodium used to be 190. All right, and neon here is 38. Wow, that's terribly small. Oh, because these are not bonding radii. Oh, I'm sorry. Did I show us the wrong one? Okay, well, whatever. If we take a look at the ionic radius of these, we see sodium has plummeted down to 116. And we see that, where's chlorine? Where did it go? 167 is its new radius. Let's see what it used to be. Is this the right one? No. These are covalent radii. This is the table we're looking at. We're looking at 79. So it's gone from 79 to 167. So huge increase as it's gone. Although I think because these are crystalline solids, they're going to be a little bit different. However, the trend here is the same. We're seeing that our atoms that we'd expect to be bigger, like sodium and fluoride, have the same number of electrons. They both have neon's electron configuration, right? But we see here that sodium actually has a smaller radius now than the fluoride ion. And that's smaller still than oxygen's. And it's bigger than magnesium as we go along. So we see here, as we keep losing electrons, we keep getting smaller. And as we gain electrons, we get bigger. So these are technically more analogous to covalent radii, which are not what I had shown you. I had shown kind of theoretical atomic radii before, so let's not worry about those. Let's worry about the trend, though. That's what's happening here. Notice the difference. Sulfur plus 4 versus 2 minus. Look at that difference. Like, it's huge. Huge, huge, huge difference. And so the reason for all these is the same. As we are losing electrons, our atomic size gets smaller. As we gain electrons going the opposite direction, we get bigger. So that's, let's swap that back. And so, if we want to take a look at those, the trends are the more positive you are of an ion, the smaller you are. And the more negative you are, you get bigger. And we're going to see that we can compare these when they are kind of the same electron configuration. So just to keep us aware, we can compare ion size between ions with the same electron configuration. We call this an isoelectronic series. That's the fun word here. So that would be something like what's after sodium magnesium? That would be something like this. This is an isoelectronic series. All these have 10 electrons. Right? And we're going to see that this one will always be the smallest, and this one will always be the largest. So your most negative of an isoelectronic series will always be the biggest one. And the most positive one will always be the smallest. Right? The reasons being you get smaller because you have now the same number of shells as everyone else, but you have more protons. More protons means things are going to be more attracted, and they're going to come in. So your effective nuclear charge increases once you kick out some electrons. And it's the opposite trend farther down. Because you get more and more electron repulsion, the more electrons you have, that tends to spread things out. It makes things expand so they can get far away from each other. All right, and so we see here that as a result of all these things, we end up being able to make these kind of comparisons within an isoelectronic series. All right, so typically, though, we typically kind of will sometimes omit this, the noble gas, because we can't really measure these very easily, because usually when we are making these, calculating these numbers, we do it when they're bound to different things. Neon doesn't ever bind with something. So we don't really know neon's actual atomic radius. We can do some calculations, and that's where that whatever 43 or whatever number comes from. But that's not really a reliable number per se. So oftentimes we will just get rid of your noble gas, and you'll just be comparing them directly as is. All right, so these are all isoelectronic with each other. They all have neon's electron configuration, and we can very clearly make the distinction. And again, number-wise, I have the numbers here. If we were looking at oxygen, again, we're looking at about 126 picometers, fluoride, 119, sodium, 116, and magnesium, 86. So we see here pretty obvious trend, right? So as we go through this. All right, so for an isoelectronic series, your smallest one is always going to be your most positive. Your largest one will always be your most negative. So there's our trend. More positive equals smaller. More negative equals bigger. All right, and so that's what we're looking at here. All right. Cool. I only have one more trend I want to talk about today. Just because this week is a little bit shorter. We'll give you guys a little bit more of a break here. We'll have shorter classes this week. The last trend we have, and this material is not terribly difficult either. There's not calculations that we have to do. There's not all those thermochemistry fun things happening. So, yeah, this week will be a little bit easier on us. Plus, I know a lot of you are catching up on your electron configuration anyway, so though you'll see this afterwards. All right, let's take a look at our next trend. The ionization energy. And we're going to see that the trend that we're going to focus on is the first ionization energy. And let's take a look at what those mean. The delta H for this reaction is the ionization energy. That's the delta H for this reaction. So it's the energy needed to lose one electron. This is always an endothermic process, which means that delta H is positive. Delta H is always positive for this. And this particular one is the first ionization energy. The second ionization energy is the delta H for the following reaction. This would be our second ionization energy. Delta H, the value of delta H is our ionization energy. So the first ionization energy, you lose your first electron. Second ionization, you lose your second electron, etc. And so, that out. Second ionization energy is you lose your second electron. And so, we're going to see here, just if you think about it, the energy for sodium to lose one electron versus for it to lose two electrons, rather to lose the second electron, we would expect the first one to be relatively low, right? We know sodium wants to lose its electron, so it's going to be a relatively low energy process. But to lose a second electron would be terribly unfavorable, right? Sodium doesn't make +2. That doesn't happen. Sodium only has one valence electron. Once it loses it, it's already got its noble gas happiness, and it's good to go. But we see here that the second ionization energy could happen, but we're going to see it's much less favorable. So let's pop over to ionization energy on our good friend Wikipedia. Swapping back over. Let's see here. Where's this nice table for us? Aha! So here's a couple of them. So if you look at sodium, the amount of energy for it to lose its first electron is about 500 kilojoules per mole. To lose the second one is almost 10 times that amount. It's incredibly unfavorable for it to lose the second electron. However, if we look at magnesium, magnesium has 2 valence electrons. It's going to say, oh, okay, I could lose my second one. That's okay. But going to the third one, oh, big jump. Not likely to happen. Aluminum, we know, forms +3 ions, relatively low numbers, big jump. Silicon, big jump. So we notice here, after we have kind of lost our last valence electron, we skyrocket up. We skyrocket up here. And of course, we have this giant leap for sulfur. Notice chlorine, to lose its 7th one, it's kind of like whatever, because then it's going to reach a noble gas, but to lose an 8th electron would just be ridiculous. So let's look at the trend. In the first ionization energy, we see that it roughly goes up as we go down the periodic table. I'm sorry, this is actually to the right. As we go down this table, it's really to the right. We have a couple of interesting anomalies that we'll talk about as we go across here. And we'll get there. So we'll talk about all these and why we have some small little dips here. So let's see, do we have any other big data tables here? I was hoping we would. Oh well, I guess this is all we have. So with this, swap back over. We have, generally speaking, we have 2 trends. We have that the first ionization energy increases left to right. Easier for sodium to lose an electron than it is for magnesium, because we're going to make sodium into a noble gas configuration, but not magnesium. And we're also going to see, as we go down the periodic table, it will decrease as we go down. It decreases as we go down. If we think about the potassium, here's a hydrogen, here's a lithium, here's a sodium. These all are going to lose 1 electron. Right? The sodium ones is much farther from the nucleus, so it's less attracted. And that means it's easier to remove. So we're going to see lithium, and lithium will have a higher first ionization energy than sodium will, and lithium will be higher than hydrogen. I wonder if I've got numbers for those here. Oh, I kind of do. So I'm going to check if I have, I do have a much bigger table. Okay, here we go. Oh my heavens. Let's see, this is a lot of numbers. All right, but let's just take a look here. Let's look at lithium. First ionization energy, 520. Hydrogen, 1312. Right, much higher. So the lithium is 520. Let's find sodium. Sodium a little bit less, right? Because as we go down, it's easier to remove. Let's look at potassium, even less as we go down. Rubidium, 403. So these go down as we go down the periodic table. And as we go to the right, generally they will also increase. So it increases going down, and it decreases going down and increases as we go to the right. Which means that we have the highest first ionization energy at helium. So that means that helium has the highest first ionization energy. And that makes sense, right? Helium is our smallest atom. That means its electrons are closest to the nucleus, meaning they're harder to remove. Francium, then, it's easy to remove francium's electron, relatively speaking. All right, francium's the biggest element. Its one valence electron is way out there. Something to pluck it off, it's done. It's gone. Easy. No problem. Helium, though, being the smallest, has its very tightly held electrons, and so it's not likely to remove those. All right, so that's the trend here. We see a couple more trends, generally speaking. And I'm gonna copy some numbers here, so we can see the trend. So I'm gonna go lithium, beryllium, boron, nitrogen. Oops, I forgot carbon. And then we have neon, right? I'm gonna put the numbers out, and we're gonna look at some of the trends. So 520, 899, 801, 1086, 1402, 1314, 1681, and then 2081. So, of course, we do see it generally increases as we go left to right, but we have some special things happening here. It actually decreases at these 2 points. Why does it decrease here? Why does it technically decrease here? The reason for this is because electrons are kind of happiest in either completely full orbitals, half full orbitals, or in empty orbitals. And what I mean by that is if we take a look at these electrons, if we think about nitrogen, its p electrons are half filled, right? And oxygen's, it's got, oh, see if we can, oh, I think I might have to delete it. Yep, okay. Make it a little bit bigger. Oxygen, if we lose one electron from oxygen, it now will have a half-filled orbital. Its p orbital will be half full. That's a happy state. Electrons like that. They like to be in half-full orbitals or empty ones. Notice boron, if we remove its electron, it will empty that orbital. That's a good thing. Electrons like that. They like to be in half-full, full, or empty orbitals. So if we remove boron's electrons, a little bit easier. All right, and if we lose oxygen's electron, a little bit easier than losing one of nitrogen's, because we end up with a slightly happy state. And interestingly enough, this is the same reason that some atoms have bizarre electron configurations. Like copper actually takes the configuration of 4s13d10 because it gives it a full d orbital. That's why this is a little bit strange. If you look these up, you'll see. What's another one? I think 1, 2, 3, 4, 5. I think chromium is another example. does something interesting. It actually, we would expect it to have, we would expect 4s2 3d9 or 4s2 3d4, but because of this kind of special happiness, or rather a little island of stability, when things are full or half filled, um, especially these larger orbitals. So p orbitals, yeah, you see a little bit of difference here between nitrogen and oxygen because you have with a half-filled p orbital. That's pretty good. But we're going to see that the d orbitals even more like to be half-filled, and so good stuff there. So that's why we see a little bit of blips there, is because we're going from oxygen, which has 4 electrons in 3 different p orbitals, to effectively nitrogen's electron configuration, which has nice half-filled orbital. And so we see some nice little dips in those. All right, so that's why. All right. All right, so that's as far as I want to go today. Next time on Thursday, we'll continue on. We will do more trends. Let's see, we'll go through electron affinity. We'll talk about kind of, it's like groups in the periodic table. And I don't think we talk about electronegativity yet. I'll have to double check, but those will probably be the trends that we'll cover next time. And that's it. It's a pretty short chapter, so so we'll go from there. Alrighty. Enjoy your day, everybody, and de-stress. We've got some electron configuration homework coming up, so make sure you get on that. That's from last week's videos, and I'll probably post this one later on so you can start looking at that. All right, cool. Take care, everyone.